Welcome to lecture number 4 for ECE 320, Digital Electronics. Today we're talking about semiconductors. Now, semiconductors are a key element for many electronic devices. It has properties that are very different from other elements like metals. For example, so here I have an inductor. At DC, an inductor is basically a bunch of copper wire. That's a metal. The DC resistance of the inductor is 56.1 ohms. What happens when I heat the inductor? Well, I've got a hairdryer right here. That doesn't work. Okay, trying that again. I have a hairdryer here. Heat up the inductor, and the resistance is going up. Not a lot, but for metals, resistance goes up as temperature goes up. Now in contrast, I have a thermistor. That's a temperature-controlled, or temperature-sensitive resistor. A thermistor is a piece of semiconductor, piece of silicon. As I heat that up, here's what happens. Notice the resistance is dropping, and it's not subtle. There's a huge drop in resistance with temperature. So for semiconductors, the resistance changes by going down as temperature goes up rather than up like metals. And the change is huge. Why is that? What property of semiconductors makes that happen? Here's another type of semiconductor. So this is a cadmium sulfide, or CDS, light sensor. It's another type of semiconductor. When I hit it with light, I have a low resistance. As I put a shadow over it, the resistance goes up. So photons reduce the resistance. Again, why is that? Why is it for semiconductors, heat or light reduces the resistance, whereas for metals, the resistance goes up as temperature goes up? In addition, semiconductors have two types of charge carriers. For metals, they only have one type of charge carrier, electron, whereas semiconductors have two types of charge carriers, holes and electrons. Basically, semiconductors are different than metal. What we're covering in today's lecture is why does silicon behave that way? Also want to know what are holes and electrons, and what can you do with silicon? So going back to chemistry, here's the periodic table of the elements. In the far right-hand column, you've got the noble gases. These are the inert gases. They don't interact with other atoms. They don't want to give up electrons. They don't want to accept electrons. If I go one to the left, I have the strong oxidizers, the halogens. They will rip electrons away from other atoms, strong oxidizers. If I go one to the right, that brings you over to here, to metals. And right in between, you've got the semiconductors like silicon and germanium. Now, the way the elements behave is like this. If I look at neon, that's one of the elements in column 8A, the noble gases. Neon has 10 protons and 10 electrons. The 10 electrons fill two shells. The inner shell has 2 electrons. The outer shell has 8 electrons. All the shells are filled with electrons. What that means is neon doesn't want to give up any electrons. It doesn't want to accept any electrons. It's happy where it is. That makes neon a noble gas, an inert gas. It doesn't interact with other elements. It also means that it does not conduct electricity. There are no free electrons to carry charge. If I go to one to the left, I get things like fluorine. That's the halogens and nonmetals like oxygen, or nitrogen. With these, each atom only has 7 electrons in the outer shell. So what they do is they form covalent bonds. They will share one of their electrons, making a diatomic molecule. The result is similar to a noble gas molecule. It's a gas, meaning low molecular weight. It doesn't conduct electricity. There's no free electrons. They're also strong oxidizers. If there's a innocent bystander like a piece of metal around here, the fluorine will rip an electron away from that metal, to fill its covalent bond. If we go the other direction, to the right, I get things like metals. If I look at sodium, neon plus 1 is sodium. That has the 10 electrons just like a neon atom plus 1. So those 10 atoms on the inner shells are all filled. The sodium atom doesn't want to give up any electrons. It doesn't want to accept any more electrons on those inner shells. Those are all filled. That 11th electron, it's electrically tied to the atom. Again, electrons are minus charge. The nucleus is plus charge. I have 11 plus charges. I need to have 11 minus charges to be neutral. But that 11th electron isn't really tied to any particular sodium atom. It's free to move throughout the crystal. That makes sodium a very good conductor of electricity. These electrons can move, and we call that the conduction band. They conduct electricity. Now, a property of metals, as I kind of demonstrated, is the resistance goes up as temperature goes up. And it depends upon the metal. The most sensitive is beryllium. The resistance goes up by 2.5% per degree C. The least sensitive is neodymium, 0.16% per degree C. Copper, that's what a lot of our wires are. Resistance goes up by 0.43% per degree C. And again, that's what you saw at the beginning video. As temperature went up for the inductor, the resistance went up. Not by a lot, but it did go up. The reason for that is, going back to the sodium example, if I'm at really low temperatures, like 0 degrees Kelvin, the protons aren't moving. The electrons can then travel unimpeded. That's superconductivity. As temperature goes up, these atoms start moving around. And as they move around, they interfere with the electron transport. So that's why for metals, resistance goes up as temperature goes up. Now for silicon was very, very different. The resistance went down, and it wasn't subtle. It went down a lot as temperature went up. The reason for that is this. Silicon is in column 4 of the periodic table. What that means is any given silicon atom has 4 electrons in its outer shell. To fill the outer shell, it forms covalent bonds, and this is kind of drawn on paper as a square. It's actually a tetrahedron, but still, each silicon atom has 4 neighbors. What that means is at low temperatures, all the electrons are in covalent bonds. There's no free electrons to carry electricity. As temperature goes up, what happens is some of the electrons will gain thermal energy and escape their covalent bond. At that point, I have a free electron. That free electron has got no place to go, so it's free to move throughout the crystal. I have a charge carrier. So as temperature goes up, I get more charge carriers, more electrons, and more charge carriers means less resistance. In addition to electrons, I get things called holes. A hole is a missing electron. Holes can also move. If I have thermal energy, this electron can jump out of its covalent bond, fill that hole, leaving a hole right here. Then this electron can jump out of its covalent bond, fill that hole, and now the hole's gone left. So holes can move, electrons can move. For semiconductors, I have 2 ways to carry charge, holes and electrons. And electrons are negative charged. Hole is a missing electron, so it's like a double negative. Holes look like a plus charge. Electrons look like a minus charge. They both carry charge. And that's actually really important. Now, the mobility of holes and electrons are different. Electrons have a higher mobility, not surprising because once you have a free electron, it just moves throughout the crystal. Holes have a lower mobility, meaning higher resistance, because there's more involved with holes moving around. For a hole to move, I have to have an electron escape its covalent bond, fill a hole. Then another electron that escapes its covalent bond, fills a hole. So the mobility of holes is less than electrons. That really doesn't have a huge impact. When we get to doping, that just means I have to dope p-type silicon 2.6 times more than n-type silicon. That's not a big deal. From a practical standpoint, what that means is actually have two types of charge carriers, electrons and holes. That's important. So let's calculate the resistance of a piece of silicon at 300 degrees Kelvin. The conductivity is due to both electrons and holes. At 300 degrees Kelvin, the number of holes, number of electrons is both about 1.5 times 10 to the 10th per cc. Seems like a big number, but you got to remember, Avogadro's number is 6.02 times 10 to the 23. That's the number of atoms per cubic centimeter. That's actually the number of atoms in a mole, which is about 1 cubic centimeter per silicon. This is the number of atoms. At room temperature, I have a few electrons escaping their covalent bond. That's about 10 to the 10th. So this is like a 10 to the 13th to 1 ratio. Very, very few atoms have lost their electron, but they are there. That does affect the resistance. The conductivity is the number of charge carriers times the charge per carrier times the mobility. And here I've got both electrons and holes. If the number of charge carriers, I guess let's call it 1.6 times 10 to the 11th. 1.6 times 10 to the 11th. Is that the mobility, or charge per carrier, is a constant. 1.9 times 10 to the minus 19 coulombs is the charge per one electron. And I have both electrons and holes carrying charge. The total mobility, or conductivity then, will be 4.78 times 10 to the minus 5, 1 over ohm centimeters. Or flipping it, the resistivity is 20,917 ohm centimeters. Basically saying that pure silicon is a poor conductor at room temperature. Suppose, another example, one find the resistance of a piece of silicon at 293 Kelvin, or at this temperature. With the length of 1 millimeter and a cross-sectional area of 0.5 by 0.5 millimeters, basically an 0402 resistor. The equation for resistance is the resistance is resistivity times length over area. This is the resistivity we just calculated. The length is 0.1 centimeter, and there's the area. That would be an 836 kilo ohm resistor. Now, as we saw with the demonstration, for pure silicon, as you heat it up, the resistance changes. That lets you build thermistors. Now, the number of free electrons is a function of temperature. So this is the number of free electrons per cubic centimeter. A0 is a constant. T is the temperature in degrees Kelvin. Eg is the energy gap for silicon. Is relatively this, it's function of temperature. Or at 300 Kelvin, the energy gap is 1.1. K is a constant, and solving I get at 300 Kelvin, I should have 1.7 times 10 to the 11th free electrons. And 300 Kelvin is, let's see, 273, 27 degrees Celsius, right here. So that's this number. As the temperature changes, the number of free electrons changes. That's what this graph is showing. And it's not subtle. As temperature goes down, the number of free electrons goes down, and the conductivity goes down accordingly. As temperature goes up, the number of thermal electrons goes up as well, and the resistance drops. That allows you to build thermistors. So for example, suppose I want to design an 0402 resistor with silicon doped at 10 to the 16th atoms per cubic centimeter. We'll get to that in just a sec. Basically says that this is low R, say 0.1 ohm. This is low R, 0.1 ohm. Here's the piece of pure silicon. How large does that piece of pure silicon have to be so that the resistance is 1 kilo ohm? In that case, I've got the resistivity is 1 over conductivity. That's what we had before, 20,917. Resistance is resistivity times length over area. I want that to be 1,000 ohms. I know resistivity, I know the area, find the length. Length is 119 microns. So if I take a piece of silicon and have this piece right here being 119 microns, I'll have a 1K thermistor. And that's really what the thermistor is that I used before. It's just a really thin piece of silicon. As temperature changes, I get more or less charge or thermal electrons. As the number of thermal electrons change, the resistance changes. Note that the resulting resistor is sensitive to temperature. Again, as temperature changes, again, this is in Kelvin, not Celsius. 0 degrees Celsius is the freezing point of water. Silicon doesn't care about the freezing point of water. 0 degrees Kelvin, that is important. So actually here, this is T in Kelvin. The number of free electrons varies with temperature. That affects the conductivity, that affects the resistivity. And if I go through all that and calculate, say temperature goes from -40 to +40 Celsius, convert to Kelvin, here's my constants, here's the intrinsic carrier concentration. If I plot the intrinsic carrier concentration versus temperature, that's what I get. Once I know the intrinsic carrier concentration, I can find the conductivity. 1 over that is the resistivity, and then the resistance. Plotting temperature versus resistance, that's what you get. And that's what we saw at the start of the lecture. As I heat up the thermistor, the resistance drops, and again, it's not subtle. I'm going from like 1 kilo ohm down to 500 ohms, down to 100 ohms. It's a big change. That also works for light sensors. If I have a light sensor, what happens is a photon will kick the electron out of the covalent bond. When I do that, I get an electron and a hole. The more photons, the more charge carriers, the less the resistance. And again, that's what we saw with the CDS light sensor. More light means less resistance. So that's one use of semiconductors. I can build a temperature sensor. I can build a light sensor. There's a thing called doping. With doping, I can change whether the material is N-type or P-type. I can also build resistors. Now, the idea of doping is, for silicon, the number of electrons times number of holes is a constant. That's the intrinsic carrier concentration. And what happens is if I have more electrons, the electrons will kind of fill up all the holes. So as the number of electrons goes up, the number of holes go down. Or vice versa, if I have extra holes, the number of holes goes up, and the electrons keep on getting sucked up by the holes, the number of electrons goes down. With silicon, I can do a thing called doping. What doping does, that lets you control the number of electrons and the number of holes in the silicon, piece of silicon, and I can control whether it's N-type or P-type. So for example, if I have intrinsic silicon right here, the number of holes is equal to the number of electrons. And it's not a very good conductor. If, however, I were to add, say, 10 to the 16th electrons to it, then what happens is, again, holes times electrons is a constant. The number of electrons has gone up. The number of holes has gone down accordingly. Now the number of electrons dominate. Almost all the charge carriers are electrons. And again, it's not subtle. There are a few holes in here, but that's, like 10 to the 12th to 1 ratio. Almost all the charge carriers are electrons. If I were to change the number of holes, make that 10 to the 16th, then the number of holes shoots up and the number of electrons shoots down. Almost all the charge carriers are now holes. And the way you do that is you dope it with different atoms. Boron, for example, has 3 electrons in the outer shell. So if I have a piece of boron, it's got the 3 electrons. When I place it in a piece of silicon, it's missing that extra electron. So I've just created a hole in the crystal. If I dope with phosphorus, phosphorus has 5 electrons in the outer shell. 4 of them fill the covalent bonds, and that extra electron has got no place to go. That creates extra electrons. That makes it N-type silicon. Now, if I dope with boron, suppose the doping is 10 to the 16th. Now the conductivity is charge per carrier, constant. Number of electrons times mobility of electrons, number of holes times mobility of holes. And notice these are so different in size, I can basically ignore that number. It's not going to have a huge impact. So the conductivity is almost all based upon the number of holes. It becomes 0.8 ohm centimeters. The resistivity is 1.25 ohm centimeters. And taking that same 0402 resistor, what used to be something like 300,000 ohms is now 50 ohms. So by doping, I can make the resistance much, much smaller. I can in fact make the doping anything I want. This doping right here, 10 to the 16th, again that looks like a large number, but again, refer to Avogadro's number, that's 6.02 times 10 to the 23rd. That's roughly the number of electrons in a cubic centimeter of silicon. That is so much bigger than 10 to the 16th that this doping is almost irrelevant from a structural standpoint, a mechanical property standpoint, crystal standpoint. It does have a huge impact on its electrical properties though. I went from 100,000 ohms or 800,000 ohms down to 50 ohms. And by varying this number, I can vary the resistance. So basically, I can build any resistor that I want using doping. If I did the same thing with phosphorus, phosphorus has 5 electrons in the outer shell. So what happens is I have 4 electrons filling the covalent bonds. That 5th electron has no place to go. That creates an N-type material, extra electrons carrying charge. Same thing works if I dope with phosphorus. Now the number of doping atoms is 10 to the 16th. That's basically the number of electrons. There are a few holes, because N times P is a constant. That's so small relative to the number of electrons, you can usually ignore it. Recalculating my conductivity and resistance, my resistor becomes 19 ohms. And kind of note that for P-type silicon, it was 50 ohms. N-type silicon was 19 ohms. That's actually not significant. The doping is so small relative to the number of silicon atoms. All I have to do is increase the doping by 2.6 times for P-type, and it's also 19.2 ohms. So again, that's not a big deal. But what is important is I have 2 types of resistors. I have P-type and N-type. In P-type, almost all the charge carriers are holes. In N-type, almost all the charge carriers are electrons. That's really important. That's going to let us build other devices, like a diode, transistor, MOSFET, semiconductor relay. But for now, if I just have a piece of N-type material or P-type material, what I can do is I can now build a resistor. So what you have is, with intrinsic silicon, I can build a thermistor. That's a temperature-sensitive resistor. I can build a light sensor, like a CDS cell. With doping, I can build a resistor and make the resistance anything I want. And I could build it out of N-type silicon or P-type silicon, either one. You really can't tell if you're using it. As an example, suppose I want to build an 0402 resistor that's 1,000 ohms. Going backwards, I want the answer to be 1,000 ohms. So given the dimensions, I know the resistivity. Whenever that's the conductivity, I can now pick. Do I want to use N-type or P-type? It really doesn't matter. If I say N-type, then the mobility is 1300. I can solve for N. And here's the doping that I need to make a 1,000 ohm resistor. That's an 0402 with these dimensions. And likewise, pick any resistor you want. If you want to make a 10K resistor, make the doping 10 times lower, gives you 10 times fewer charge carriers, gives you 10 times higher resistance. It's really easy designing resistors with silicon. So in summary, semiconductors are very, very different than metals. Their resistance goes down as temperature goes up, unlike metals where resistance goes up. That allows you to build thermistors. They have two types of charge carriers. They have electrons and holes, unlike metals that just have electrons. Now with that, I can build, with doping, I can set the resistance of a piece of silicon. I can make an N-type semiconductor, where almost all the charge carriers are electrons, and I can make a P-type semiconductor, where almost all the charge carriers are holes. What you can do with that comes up in the following lectures. That's basically, if I just have N-type, P-type, I've got a resistor. If I have P-type coupled with N-type, that's a diode. If I have three of them tacked together, NPN or PNP, that's a transistor. If I have four of them tacked together, that's a semiconductor relay. And there's one other one. If I have an N-type, two little islands of N-type and a P-type material with a piece of aluminum on top, that's a MOSFET. So again, the N-type, P-type are all important. That's what allows us to build almost all the electronic devices we'll be talking about in this course. So that's lecture number 4 for ECE 320, Digital Electronics.